Hi everyone, welcome back and thank you for joining us again. In this video we're going to continue our discussion of basically introducing astronomy as a science to our folks, and here we're going to discuss pretty much our modern view of the universe. We already talked about the scale of the universe and putting everything in perspective, and now we're going to look a little bit more about our place in the universe in terms of its history, the expansion of the Big Bang, and the elements of life. So, as you know, we live on Earth, which is among at least 7 other planets in our solar system that orbit the Sun. And our solar system itself is one of many in the Milky Way, among one of about 400 other billion solar systems, or at least stellar systems, that orbit around a common center. But the Milky Way itself continues in this sense. In other words, it's part of a small cluster of galaxies called the local group. The local group is composed primarily of the Milky Way and the Andromeda Galaxy, and to some extent the Triangulum Galaxy, i.e. M33, and all of their satellite galaxies. Now, the local group, this small cluster of galaxies, this itself is part of the Virgo supercluster of galaxies. And for a while we thought that the Virgo supercluster of galaxies was the largest entity with which we were gravitationally associated. But in 2014, around that time, we realized that even the Virgo supercluster is part of an even larger supercluster called the Laniakea supercluster. And galaxy superclusters like this are the largest gravitationally associated entities in the universe. So, I should mention that what we're about to discuss is not a definitive history, and in other words, it's only a very brief introduction to a whole lot of ideas that we're going to discuss in a lot more detail throughout the rest of the course. So, in the 19-teens, astronomers started finding hints that the universe was expanding. They noticed that certain objects called spiral nebulae always seemed to be moving away from Earth, or at least away from our solar system, and that the fainter these things were, the faster they seemed to be moving away from us. And in the 1920s, this was put on a very definitive footing with the discovery that these spiral nebulae are actually galaxies, and they're located far outside of the Milky Way. And then this discovery was made by Edwin Hubble. That was his first major discovery. And then his second major discovery was the discovery that there actually was something kind of resembling a linear relationship between a galaxy's distance from us and the rate at which it's moving away from us. One, they were pretty much all moving away from us. The only exceptions to this were galaxies in the local group. And two, the rate at which they're moving away from us is roughly proportional to their distance away from us. And of course, we're going to discuss this in a lot more detail. This led to the concept of the Big Bang, especially when this was put on a mathematical footing with the help of general relativity. So, the Big Bang. And again, we have an entire unit on cosmology, so we're just hitting the very brief details here. So, the heat from the Big Bang itself was too intense to allow nuclear fusion until about a second after the Big Bang. Before that, all you had were protons and neutrons, and even up until about a millionth of a second after the Big Bang, you couldn't even have protons and neutrons. But once the universe had cooled enough, which happened about a second after the Big Bang, protons and neutrons were able to stick together to form deuterium nuclei without getting busted apart by big, heavy, powerful gamma rays. I say heavy because they're very energetic. They don't have mass. But after that, thing is, the universe was too cool to really fuse much heavier nuclei. You were able to get helium-3 and helium-4 out of this Big Bang nucleosynthesis, as we called it, and you could also get lithium-7 and beryllium-7, though beryllium-7 is unstable, all of that decayed, but you couldn't get anything heavier than that. In other words, anything heavier than that either formed in stars, or as a result of stellar explosions, or as a result of the breakup of heavier stuff that formed in stars or stellar explosions. So, in other words, other than hydrogen, helium, and small amounts of lithium, everything that's with us today was not created in the Big Bang. It was created later. So after that, the universe was a very boring place for a long time. Up until about 400,000 years after the Big Bang, light couldn't even travel without bouncing off of all kinds of electrons. And then even after that, it took about 100 million years or so for the first stars and galaxies to form. And then after that, galaxies continued forming and merging with each other and colliding, and big galaxies like the Milky Way formed through a variety of collisions after their initial formation. So in other words, you get big galaxies by absorbing little galaxies. And this type of process is still ongoing today, such as in Stephan's quintet right here, and the antennae galaxies right here. A very nice picture of a couple of galaxies that are in the process of colliding. And even the Milky Way is still going to be participating in this process. In about 4 billion years, we're going to start colliding with the Andromeda Galaxy, and we will eventually merge with the Andromeda Galaxy. And perhaps a few billion years after that, the Triangulum Galaxy might end up joining us as well. Another thing to notice in this nice picture is that a lot of these really deep Hubble Space Telescope pictures show a number of other things. For example, you have a lot of these background galaxies here, galaxies that are probably hundreds of millions of light years away, whereas the antenna galaxies are just tens of millions of light years away. Yeah, tens of millions of light years away for galaxies, we would consider that the local universe. Now, stars, after they form, they start producing heavy elements. They do that through the process of nuclear fusion, and that's something that we're going to get to in a lot more detail later in the course. But long story short, after hydrogen ends up forming into helium in stellar cores, many stars start fusing helium into elements like carbon, nitrogen, and oxygen, and even bigger stars will start fusing into neon and magnesium, etc. Now, most stars during the later stages of their lives, or, well, at least I should say most sun-like stars during the later stages of their lives, when they cast off their outer layers, or at least right before they do that, they start producing a number of heavy elements. They don't produce huge amounts of these things, but they do produce small amounts of a whole bunch of the heavy elements, especially like the lanthanides and similarly heavy elements on the periodic table. But if you want a whole bunch of stuff, you're going to have to rely on supernova explosions. That's where you get huge amounts of iron and heavier elements as well. Supernova explosions, neutron star mergers, that sort of thing. In other words, heavy elements are generally produced in stars. In fact, anything, as we mentioned, heavier than lithium is generally produced in stars. Exceptions are beryllium and boron. The beryllium and boron that's in the universe today is generally produced by things like cosmic rays smashing into heavier nuclei and creating lighter nuclei as a result. In other words, splitting them apart. Cosmic ray spallation is what we call that. But in any case, yeah, we are basically star stuff, in the words of Carl Sagan. In fact, a lot of this stardust it goes into the rest of the galaxy, and it can pollute other giant molecular clouds that haven't quite collapsed by their own gravity to form stars. And in one particular case, about 4.57 billion years ago, our solar system was born in such a collapsing gas cloud. And the vast majority of atoms in the universe were created either inside of stars or during the Big Bang, including pretty much everything in our solar system, except for, as I mentioned, beryllium and boron. But the main point I want to make in this situation is the chemical reactions do not create elements. Chemical reactions create chemicals. Now, the molecules of life. Amino acids form part of the basis of life as we know it, and this formation of molecules, chemistry, does seem to happen in what we call the interstellar medium. Again, we're going to get into this in a lot more detail later in the course. But as it turns out, meteors have been found to contain all of the amino acids that are necessary for life as we know it, as well as a whole bunch of other what we call useless amino acids. So you kind of wonder, it's like, well, maybe life as we don't know it might make some use of those. Now, on our planet, life began about 3.7 to 3.8 billion years ago or so. There is, I should mention, some tentative evidence that perhaps life might have been around at about 4.14 billion years ago. There there have been some interesting chemical analyses of rocks that indicate that that might have been the case. If this turns out to be true, that might end up being perhaps the biggest scientific discovery of the past 100 years, because that would show that there's a pretty high chance that life formed twice on our planet and was driven to extinction and then formed a separate time. And so far we had previously had no evidence of that, but this would be very strong evidence in favor of that, because about 4 billion years ago, as we'll discuss in the solar system unit, the inner solar system suffered what we call the late heavy bombardment, where, due to certain things that happened in the outer solar system, which again we'll get into more details later, the inner solar system was bombarded with lots of very large asteroids, and this would have caused the extinction of any life that was already around on Earth. But if there was life 4.14 billion years ago, and we know that there was life later, then this would mean that life formed twice on our planet. So that would be an incredibly significant scientific discovery if this ends up being confirmed. Now, about particularly peaking about 2.5 billion years ago was oxygen photosynthesis. It was actually at 2.5 billion years ago that there was a sudden increase in the amount of molecular oxygen in our atmosphere, and that nearly killed all life. Only oxygen-tolerant organisms, or those living in deep sea vents, were able to survive this oxygen catastrophe, the Great Oxygenation Event, as it was called. Now, after that, still, life was relatively boring on this planet. The first animals didn't come around until about 600 million years ago. And these were soft-bodied organisms. In fact, none of those remains of those hadn't even been discovered at the time when Charles Darwin lived. This was something he considered as a major weakness in his evolutionary theory, trying to explain the Cambrian explosion, where you suddenly had all of these complex life forms seemingly appearing suddenly in the fossil record 535 million years ago. Well, turns out there actually were soft-bodied organisms before that. It's just that they're not fossilized very easily, but they had not been discovered during the time of Darwin. Again, we'll get back to that later in the course. And what about mammals? Well, the ancestors of mammals really started taking shape about 300 million years ago, and Dimetrodon was a particularly ferocious creature that lived around that time, and it was of the line that would eventually become mammals. This thing was about 10 feet long. And here's kind of another image of this. And dinosaurs developed from a group of reptiles called archosaurs. We still have archosaurs around today. Crocodilians are a type of archosaur, as are birds. Birds evolved from dinosaurs, as you may know. But mammals really also developed at about the same time, though dinosaurs generally kind of dominated the ecosystem. But then, around 66 million years ago, there was a major mass extinction, the most recent major mass extinction, when an asteroid crashed into Earth. And in fact, now we recognize that it probably was just one asteroid around the Yucatan Peninsula of Mexico. And this event was something that was a very major catastrophe for our planet. There was already a lot going on. This may have either contributed to or at least exacerbated the effect of a major eruption of supervolcanoes around what at that time was the Indian subcontinent, which at that time was in the south part of the Indian Ocean. But this killed off all of the non-avian dinosaurs, which allowed mammals to fill a lot of the missing ecological niches during that time. Primates started to appear soon thereafter. In fact, mitochondrial DNA sequencing shows that apes diverged from primates sometime around between about 34.5 million and 29 million years ago. And then after that, great apes diverged from lesser apes, and then the line leading to modern humans diverged from that sometime between about 5 and 7 million years ago. And in other words, one line would eventually lead to modern humans, and the other lines would eventually lead to chimpanzees. But anatomically modern humans, in other words, say like a million years or so ago, there were a number of humanoid species around, but the line that would lead specifically to Homo sapiens sapiens, which is us, with the others all going extinct, evolved in Africa about 50,000 years ago or so. And then that would eventually lead to us, trolls. So now, consider the following question. Earth is the only place we know in the universe with conditions suitable for human life. How does visualizing Earth to scale affect your perspective on human existence and your perspective on our planet? So that's something to think about. So if you want to think about that, now is a good time to pause the video. So now that you've had a chance to think about that, this is a good time to turn our attention to different matters. Motion through the universe. We've already talked about our solar system's motion around the galaxy and stuff like that, but it gets more complicated than that, more interesting than that. So some basic physics. So you know that the average speed of an object is the distance it travels divided by the time over which it travels that distance. So you can summarize that by the formula v equals delta s or delta x or delta whatever over t, where v is the object's velocity, which for our purposes we're just going to call speed. Now, what if something's going in circular motion? Well, in that case, the distance traveled is just the circumference of a circle. And you learned back when you were in diapers that the circumference of a circle is 2 pi r. Now, that means that the speed, therefore, is the distance divided by time. Well, the time to go around a circle is a special kind of time called period. So instead of calling that lowercase t, we often call that capital T. So the speed of an object going around a circle is v equals 2 pi r over t, circumference divided by period. So 2 pi r over t. That's actually a good formula to memorize, strangely enough. So the center of mass of our galaxy lies in the center of our disk. And large-scale motions of objects in our galaxy tend to occur around the galactic center, at least on average. Well, our solar system takes about 200 million years to complete one orbit around the center. But we move even more than that. In other words, it's not a circular orbit. It's not even an elliptical orbit. We're actually, as we go around, we're making kind of a sinusoidal path above and below the disk of our galaxy as we travel around in our general kind of elliptical orbit. And this occurs due to the fact that the galaxy has, in addition to a spherical mass distribution dominated by dark matter, there's also a mass distribution that's kind of planar, and we are close to that plane. So being close to that plane, we have this kind of what you might call a it's not exactly sinusoidal, but a cyclical motion above and below the plane of the galaxy. In fact, some people believe that our solar system's passage through that disk is a cause of some mass extinctions. So the jury's still out on that one. So let's practice, though, using this formula for a number of situations, including our galaxy. In fact, to be more precise, it takes us about 230 million years to orbit around our galaxy once. So first, find the speed of a point on Earth's equator, find the speed of Earth as it revolves around our sun, and then find the distance of our solar system from the center of the galaxy, given that it takes about 230 million years to go around once with an orbital speed of about 240 kilometers per second. So, well, like good students, we write our givens when solving problems, and we write the equation that we want to use, and then plug in our givens, if it's that simple. If this was, say, like a physics class, we might need to combine equations together and do some sort of derivation, but here it's a simple problem. So, we find that the speed of a point on Earth's equator during Earth's rotation is 464 meters per second. That is about like 1,050 miles per hour or something like that. Now, if you're looking closely here, you might notice that I cheated. Do you see something wrong with one of my givens? Earth's rotation period, remember, is not exactly 24 hours. It's actually about 23 hours, 56 minutes, and 4 seconds. In other words, I need to subtract 240 minus 4, that is 236 seconds from this number. So that would mean that Earth's rotation period is actually 86,164 seconds. So I rounded to 24 hours just for the sake of argument here. But the point is, yeah, you can do this. But yeah, remember, a day is 24 hours because we time the day from high noon to high noon. But we have to rotate a little bit extra in order to get the sun in the same part of the sky again, because as we rotate, we're orbiting around the sun. Okay. So what about Earth going around the sun? Well, the orbital period there is 1 year. And here I used the exact time, to 5 significant digits, the time it takes for Earth to complete exactly one orbit, 365.2 days. That's actually slightly different than the calendar year for reasons that we will discuss in a future video in this unit. But in any case, converting that to seconds and rounding to 5 sig figs gives you 3.1558 times 10 to the 7 seconds. It's actually not too much more than pi times 10 to the 7 seconds. And a lot of professional astronomers, when they're doing just rough estimate calculations, they will approximate a year as pi times 10 to the 7 because they expect to cancel a pi in their equation. So in any case, we write the equation and plug in the values, and we get that our planet is going around the sun at pretty close to 30 kilometers per second. So like 29.8 kilometers per second. What about the distance of our solar system from the center of the Milky Way? So we're trying to figure out R in this case. We're given V. We're given the period. We're told that it's 230 million years. And 230 million is 230 times 10 to the 6th years. I decided to use this notation instead of normal scientific notation because it kind of makes it easier to tell where that number came from. And converting that to seconds, we have that. And plug in V equals 2 pi r over t. And we end up getting that the orbital radius, the radius of our orbit around the Milky Way on average at least, is about 2.77 times 10 to the 20 meters. The actual distance of our sun from the center of the galaxy right now is a little over 26,000 light years. The exact number just kind of depends on who you ask, but it's somewhere between about 26,000 and 27,000 light years. So we're pretty far out. How about another example? How about the speed of Mars as it travels around the sun? Well, same idea. But here we use units of AUs for our distance from Mars, and we convert that. So we have meters. We convert the period of Mars to days because it takes 688 days to go around the sun. That's something you could look up. And then V equals 2 pi r over t. Plug in the numbers, and you get that Mars's speed is about 24 kilometers per second. Notice that that's slower than Earth's speed because Mars is farther out. Our sun's force of gravity on Mars, or at least the gravitational field at Mars, is weaker than the gravitational field at Earth. So now that you've practiced this is something that you should be able to use in the future. So keep that in mind. Now, just as we have lots of orbital motion, we also have the expansion of the universe. Now, something I do want to mention, first off, is that the expansion of the universe does not affect interactions between galaxies in tightly bound clusters. In other words, once something is gravitationally bound together, it stays gravitationally bound together, regardless of the expansion of the universe. And that's because of the fact that the amount of energy in the space between the objects that are gravitationally bound together does not change. However, when things are not gravitationally bound together, that spatial distance will end up increasing over time because of the expansion of the universe. So, in the case of our galaxy, we are kind of interacting with other members of the local group, but the local group itself is expanding away from other galaxy clusters due to the expansion of the universe, what we call the Hubble flow or the Hubble expansion. In fact, the local group, and also a whole lot of other clusters, are being pulled toward a so-called great attractor in the Norma cluster region, which we now recognize as being pretty close to the center of the Laniakea supercluster. So here is an infrared image of part of the Great Attractor, the Norma cluster. So in spite of the universe's expansion, not everything kind of expands along with that exactly, because again, galaxies can interact with other galaxies in clusters and superclusters. But as the distance scale increases, as you look farther and farther away, the expansion of the universe completely dominates over those peculiar velocities. In other words, the ratio of the speed of a galaxy or a cluster relative to another cluster due to gravitational interactions compared with the speed at which it's expanding away from us due to the universe's expansion becomes smaller and smaller as you look to farther and farther galaxies away. So, for example, the cluster Abell 1689 featured in this picture, that's 2.2 billion light years away. And due to the expansion of the universe, this thing's actually moving away from us at 47,000 kilometers per second. Now, the speed of light is about 300,000 kilometers per second. So here we're talking about a significant percentage of the speed of light. In fact, that's what kind of tells us about where the edge of the visible universe is. In other words, anything that is farther away than the so-called edge of the visible universe is expanding away from us faster than the speed of light, and its light will never be able to reach us. So now let's turn our attention to astronomy as a science. So as you know, science is built upon laws, facts, and theories. Now, laws are generalizations about things that tend to be true. Sometimes laws are pretty powerful. In a lot of cases, they are simply statements about nature that people have noted time and time again. For example, a law is that massive objects attract each other through a universal force, gravity, which is the same force that causes objects to fall on Earth. In other words, Newton's law of universal gravitation. Now, facts are simply true statements about something that is quite well defined. For example, in biology, the physical characteristics of populations of animals change when you look at different ages in the fossil record. That is simply the fact of biological evolution. Theories, on the other hand, tend to take into account facts, laws, logic, math, etc. to make a general statement about how and why something is true. And they can be used quite effectively, if they're good, to make future predictions. An example, kind of piggybacking off of my fact example, is that the observed evolution of animals, this is an example of a theory, is that the observed evolution of animals in the fossil record is due to the process of natural selection, where there's a source of variation, and animals with variations that allow them to be better adapt to their environment are favored, while those without such variations are selected against. That is Darwinian natural selection. This is Darwin's theory about how evolution proceeds. People recognized that evolution exists noticeably before Charles Darwin became a major figure, but Darwin put forth a very good theory that explains why it happens, and it's still generally considered to be the framework for biological theories of evolution. But in the same realm, astronomy is a science. Now, in truth, a lot of things that we call laws, such as Newton's law of universal gravitation, are, in a sense, theories. In other words, Newton's law of universal gravitation is a mathematical statement that says, hey, this is how objects attract each other by gravity, and this is why the planets orbit around the sun. Because if you do a mathematical derivation from that, you realize that you get elliptical orbits in the case of an inverse square law. So the laws that go into theories in physics and astrophysics are behind many of the phenomena that we will study in this course. And we can often make inferences through the use of theories. This is why theories are the big, important achievements in science, because of the fact that you can use them to make testable, useful predictions. And I should especially emphasize the fact that in science, there's no such thing as something being, quote, just a theory. That's because of the fact that the word theory has multiple definitions, and the way that people tend to use it in everyday language is very different from the way that scientists tend to use the word theory. When scientists use the word theory, they're talking about something that is the culmination of good science, that takes into account all of the facts and logic and mathematics, etc., to form a testable explanation of why something is the way it is. So, a fact is not a theory. But of course, very good theories are going to be, after a while, kind of stated as facts, or when disagreed by some people, stated as non-facts. For example, as we mentioned before, biological evolution is a fact. It is proven to be true by mitochondrial DNA sequencing, as well as a number of other lines of logic. However, Darwin's idea of evolution by process of natural selection, that is a theory. It attempts to explain how and why it occurs. Discovering that evolution occurs is a fact. It's like, yeah, that was important, it was good. But explaining why it occurs, that was what we really remember. That is what put Charles Darwin as a household name. In astronomy, we have similar situations. For example, it is a fact that if you were to imagine a highly elliptical orbit of a planet around the sun, I mean, most of the planets have orbits that are pretty close to being circular, but like, say, a comet or something like that with a very highly elliptical orbit. Well, if you were to watch that over many orbits, you would notice that the orientation of that orbit would shift relative to the background stars. We call that precession. That is a fact. Isaac Newton's theory of gravity is not sufficient in explaining that fact. In other words, his idea of gravity seems to have a hole in it. Well, as it turns out, general relativity proposes a physical explanation for that precession. In fact, it's called precession, that shift relative to the background stars that occurs over many orbits. And it explains a whole lot of other phenomena as well. So we call general relativity a theory. Interestingly enough, that precession kind of came out as a by-the-way type of thing. Einstein was surprised to find that it predicted this, and the prediction ended up matching an observation that he didn't even know about. Good theories make bold predictions that are testable and distinguish them from alternatives. In other words, it makes predictions that could potentially prove the theory wrong if the theory turned out to be incorrect. Now, we are going to, of course, examine a number of theories throughout this course. Good theories that at least seek to explain why the universe is the way it is. And in a lot of these cases, we will simply be explaining facts that some people might think of as theories, but are actually facts really when you come down to it. And the theories that represent them are more theories about explaining why those facts are the way they are. So much of astronomy is based not only on the forces and interactions between celestial objects, but also upon their motions, both real and apparent. That's why we spent a good bit of time in the last couple of videos talking about size scales and motions. And you might want to consider, what is real motion? And what distinguishes real motion from apparent motion? Is there any such thing as absolute real motion? And we will examine some of the consequences of these qualities that we've been exploring through pictures and videos and labs, as well as practice and discussions and homework throughout the course of the year. So I look forward to the rest of our discussions. Thank you.